Hello everybody. First of all, thank you very much for this wonderful opportunity. My name is Nida Ahmed, and the paper that we submitted for this conference was towards our sixth degree of freedom parallel manipulator for precise and atraumatic cochlear implantation, which was co-authored by Shang Yu and my supervisors, Dr. Ming Feng Wang and Dr. Shin Lidu. We are a research group based at Brunel University of London in the UK, and I'm a second year PhD student being funded by Royal National Institute of Deaf People. So talking about cochlear implants, what it is. So cochlear implants is an invasive procedure for people who are profound to deafness or have hearing disability. Uh, as you can see, this spiral structure in the diagram is called cochlea and is responsible for converting sound energy into electrical energy, and when it fails to do its job, the person feels difficulty in hearing. So what he or she needs to do is to go to a doctor, and a surgeon will implant a cochlear device into the ear. So cochlear device has three parts. First is called transmitter, the other which is placed outside the ear, and the second one is the receiver, which is just placed inside your ear. Here you can see a wire which is going into the cochlea is called an electrode, and which is also represented here. Electrode is the most important part of the surgery, because when the electrode is placed carefully inserted into the cochlea in a manner that it closely follows the natural curvature of cochlear anatomy, the studies show that precise electrode placement has shown significantly enhanced auditory outcomes. So what happens in a cochlear implant surgery is that before the surgery, the patient has to go to the hospital, where a surgeon will take the patient's pre-operative images using CT scan or MRI, and on the basis of those CT scan or MRI images, pre-operative planning is done. Basically, in that process, the surgeon identifies the insertion routes, the insertion depths, and etc. And then on the day of the surgery, um, the posterior part of the ear is removed, and at that point the surgeon has a choice whether to insert the electrode manually or with the help of a robot assistance. Whatever the way is chosen, the post-operative images are taken, and then they are compared with the pre-operative planning data to make sure the placement has been done accurately and then proceeds to wound closure. Now, robots has been in otology for a while. To name some, you can see here, this is a robot Hero, which is for direct cochlear implants, and Robotol is insertion robot, which is a French innovation. So, like I said, I have been working on the sixth degree of freedom parallel manipulator, and I'm designing a parallel manipulator that fixes on the head of patient on the day of surgery, which will be integrated with the impedance based feedback system. So the impedance based feedback system, what it does is it collects the data of the internal impedance of the ear and generates some results on the basis of AI that will guide and navigate the robot to change its position to reach different orientations, so that electrode can be inserted smoothly into the cochlea. Now the previous research group here at Brunel had already developed the feedback system. My work here is more related to robotics and its integration with the feedback system. The aim of my project is to enhance the electrode placement accuracy, and this is achieved by performing detailed kinematic, workspace, and singularity analysis to understand how the manipulator moves, and using analytical models, numerical evaluations, and MATLAB simulations, the design is validated to ensure that it not only fits the compact workspace of the ear, but also delivers accurate joint angles and smooth control for the whole robot. Talking about the design of the parallel manipulator, here you can see that I have a fixed base and I have an end effector. So each leg will have a prismatic, revolute, and a spherical joint. The first prismatic and first revolute joints are active. Second and the spherical joints are passive joints. So the active joints here adhere to the 6th degree of freedom. On the fixed and on the end effector, you can see a gripper or a holder which will hold the electrode and will help smoothly insert the electrode into the air. And then there's a jig which is placed just under the fixed base to place the robot accurately on the patient's skull. As I said that we have been working on the kinematics. So starting with inverse kinematics, using the known positions of the upper spherical joints, we have calculated the rotational angles for each leg of the robot. These angles are determined mathematically, and then these results are evaluated in MATLAB. As you can see in this diagram also, the robot is referenced at the height of 10 centimeter, and the result shows that it can go along plus minus 5 centimeter of height in z-axis direction. And the results also show that by changing these joint angles, the robot can reach different positions. Forward kinematics. So in forward kinematics, we have used a combination of different joint angles to calculate the end effector positions using Sylvester elimination method, and in this way we have achieved combination of angles which gives us the realistic positions, and some angles also yield unrealistic combinations which we want to avoid in a surgical environment. Now kinematic analysis here is of particular importance because on the day of surgery, the first input will be made by the first input to the robot will be made by the surgeon, where the surgeon will give a tentative input to the robot, and the feedback system will guide the robot to change its position, to change its orientation, to help insert the electrode into the cochlea using inverse kinematics. The reachability or the workspace is an important factor here to consider. So we have considered the reachability of the end effector because that is the main component which is responsible for inserting the electrode into the cochlea. So the position of end effector is determined by using the position of the spherical joints with relation to the base, and then roll pitch yaw angles are calculated, which are necessary to give a tip and tilt movement to the end effector to reach different orientations. These mathematical equations, they are implemented in MATLAB, and they are visualized. The simulation results shows the end effector moves within a spherical volume with relation to the fixed base, and it can move different heights along z-axis. Important result from this analysis was that shorter limb lengths are needed for carrying out the cochlear implant surgery, and shorter limb lengths actually help us to align with the workspace of the ear. Now the reachability of the legs is also an important thing because on the day of surgery we don't want our robot to collapse, so we have developed these equations that represent inner and outer workspace of the legs in the absolute coordinate system. This approach helps us visualize the orientation limits of each leg and volume where the Maniuplator can maintain full orientation control. Singularity analysis is particularly important because we don't want the robot to collapse or reach unnecessary orientation where it loses 1 or 2 degrees of freedom. So to avoid that, we have performed singularity analysis using Jacobian and extended Jacobian, and we have obtained a combination of angles and orientations that helps us to identify that which orientations are realistic and which we should avoid. For example, the extension and the retraction of the robots or the legs is something that we completely will want to avoid, because it will drive the robot uh, into the singular position. Currently, I'm working on the solving the design problem using machine learning, and this is my uh, first CAD design. Here you can see the robot is doing the insertion and how the legs and the actuators are helping to perform the job. So in the conclusion, I would say that we have performed the kinematic analysis, singularity analysis, and determined the workspace. And in future, I tend to rapid prototype it using 3D printing techniques and integration with the impedance sensing technique. Taking this opportunity, I would like to thank RNID for their financial support for this PhD and this research. We are also thankful to Medel for lending us Medel devices for this research, and we are closely working with a team of clinicians at Queen Elizabeth Children's Hospital at Birmingham. Their navigation and support is very much valued. These are the list of references. This is my email address and a link to my QR code to my LinkedIn. If you want to talk, or you want to have an informal chat, please feel free to drop a message, and we'll take it from there. Last but not the least, a brief introduction about Brunel. We are a university based in west of London. We have a very good research output, and we have a great outlook for international students. The academic staff here is quite welcoming, and this is my supervisor's, Dr. Ming Fang's research interest. He's particularly interested in research related to robotics, and has been working on many applications like medical robots and leg robots. So please feel free to reach out to him, and thank you very much for your time. If there's any question, I